Today I'd like to talk about the evolution of volatiles in the permanently shadowed craters in the north and south pole of the Moon. Here is a lunar landscape in the South Pole, but it's taken a month for us to be able to put it together. And what we've done is shown the total month lighting conditions in the South Pole. What we see are regions that are permanently shadowed. Now these regions, of course, are impact craters that are deep for which the sun has not been able to reach into these craters. We have realized the importance of these permanently shadowed craters holding a variety of volatiles. From orbit, our analysis seems to indicate that these may be large reservoirs of volatiles, in particular water. Now this has occurred over the history of the Moon, and in addition to water, there may be other volatiles that are in these permanently shadowed regions. Since this is a region of interest for NASA and the upcoming ARTEMIS program, we really need to understand and anticipate what kind of science that we would be able to do by getting into these permanently shadowed regions and studying the history of these volatiles that we believe are trapped there. To understand what might be available in these permanently shadowed regions, let's go back to the beginning. Let's start trying to understand how the Earth and the Moon were formed. Well, our best theory of the formation of the Earth and the Moon starts with what we call the giant impact hypothesis. Imagine 4.6 billion years ago, as our collapsing cloud is creating a disk of material that is then accumulating into these protoplanets. Around the sun in our orbit is the proto-Earth, but also other objects are accreting. We believe another object, perhaps the size of Mars, was accreting at the same time the proto-Earth was. We call that object Theia. And over time, and it's a matter of a few million years, as these objects are coming together, there's a collision between Theia and the proto-Earth. Now, upon that impact, a debris disk forms around the Earth, and it quickly coalesces to form that moon outside the Roche limit. Below the Roche limit, which is at 2.9 Earth radii, that material falls back on the Earth. But beyond the Roche limit, material can be accreted into this new object that we call the Moon. Now, due to the high temperature created from this collision, it is expected that volatiles would escape this disk, leaving the resulting moon a very dry, gas-free metal poor body. So what happens over time and how the moon then could accrete more volatiles is of interest to pursue. The next concept of after the moon is formed, in that is tidal forces between the Earth and the moon are being dissipated, and as that occurs, the moon continues to move away from the Earth. In fact, the Apollo program told us, after putting retroreflectors on the moon and us bouncing lasers off these retroreflectors every year for the last 50 years, that we can see that the moon is moving away from the Earth about 1.5 inches per year. So for instance, at 3.9 billion years, some 600 or 700 million years after the Earth and Moon were formed, the Moon may be as far as 21 Earth radii away. And in fact, today, the Moon resides at about 60 Earth radii away. Well, during the time in the formation of the Moon, when the Moon was right at or near that Roche limit, It must have been enormous. We estimate that it must have been at least 16 times the size of the current moon today. In time, over this 4.6 billion years, an event occurred called the Late Heavy Bombardment. At about 4.1 to 3.8 billion years ago, huge asteroids hit the moon. Of course, they also hit the Earth and all the inner planets. Now, we know this occurred because we have brought back samples from the moon and age datum. We have found the age of the moon at the 4.6 billion years ago, but we also see these newer impacts, these newer materials are formed from impacts at the 4.1 to 3.8 billion years. Now, these impacts are from objects that are actually quite large. 100 kilometers or more in diameter. This produces huge gouging out of the crust of the moon. In fact, the lower crust and upper mantle, which is still molten at this stage, pours into these craters, pours into what we call basins. And as it's doing so, it's also outgassing. Because this mantle material is slightly richer in metals, we then see a coloration difference between the old surface of the moon when it was formed and this new magma that is then pouring into these basins. That color difference we can see from Earth. This is really the mare that we see in these craters on the moon. What happens next is during the phase of magma flowing into these large basins area creating the mare, the moon is also outgassing. So whatever volatiles are remaining within the moon must also be percolating out. We estimate that at its peak, the atmosphere of the moon may be as large as 10 or 12 millibars. This is even larger than the atmospheric pressure of Mars today. Now, in addition to the outgassing of the moon from this late bombardment, the rock material that we brought back clearly indicates that the moon also had an intrinsic magnetic field, probably generated deep in its interior through dynamo interactions. So between 4.2 and 3.2 billion years ago, then we expect the moon to have created a magnetosphere. Now this is significant because this magnetosphere is occurring at the same time of the Earth's magnetosphere, and also the moon is much closer. Now here are some basic simulations of the Earth-Moon magnetospheres. We call this a coupled set of magnetic fields. These magnetic fields, as they couple, allow atmospheric and ionospheric material flowing away from the Earth to follow these field lines and then actually be deposited on the moon. As the outgassing occurs and the lunar atmosphere increases, we also expect some of the lunar atmosphere to flow down these field lines towards the Earth. So on the left-hand panel, when the moon is sunward of the Earth, on the day side we see how extensive the total magnetosphere is. On the night side, the moon is well positioned inside the tail region behind the Earth on the night side, but the field lines are still well connected, and indeed volatiles from the Earth's atmosphere must indeed be flowing onto the moon. Well, over time, we now have recognized that, of course, the moon lost its magnetic field. It continued to move away from the Earth. The solar wind then began to strip the atmosphere, and the moon quite quickly, within about 100 million years from its peak of the magnetosphere at 4 billion years ago, then became the arid and dry moon that we see today on its surface. Now, we also have discovered most recently that micrometeors that come and impact the moon, in particular as the Earth and the Moon system move through old comet tails or old asteroid tails, debris that is flowing around the sun in these former orbits, we see these micrometeors impacting the moon, releasing subsurface water, and it's a very small amount, but it's been going on now for billions of years. And this water, of course, is going to migrate to these permanently shadowed regions. This is what we call the current water cycle on the moon. Now, in addition to H2O, to the water, we expect that and have observed other compounds trapped in the regolith, such as nitrogen, carbon, fluorine, sulfur. Perhaps all these were Earth origin, and we now understand, based on that magnetosphere of the Earth and that connection with the lunar magnetosphere, pathways for these particles and atmospheric constituents from the Earth to actually be deposited on the moon. The helium that we expect to see embedded into the lunar regolith is probably of solar origin. So, in summary then, as we return to the moon and go to the South Pole and go into these permanently shadowed regions, we would expect a stratigraphy of volatiles to be uncovered. That as we look at these cores that we would take on the moon, we would see predominant volatiles from comets and asteroids, also from the lunar atmosphere. Also, we would expect the Earth atmosphere contribution. And then, of course, water that's coming from that current water cycle of micrometeor impacts on the moon. So these cores that we expect to do, much like what we show here from systems that were developed on Earth to obtain cores at the Antarctic and the Arctic, we expect to deploy similar instruments to the moon to be able to create cores and then interrogate them, looking for these volatiles so that we can understand that overall history of the volatiles in the permanently shadowed region and the evolution of the Earth and lunar atmospheres. Now that's going to be done via the ARTEMIS program. And the ARTEMIS program is designed to be able to put the first woman and the next human, could be a man, could also be a woman, on the South Pole by 2024. And this requires a variety of missions to build up to that. The first one, Artemis 1, will have the Orion capsule launched by the Space Launch System, which will orbit the moon and come back, much like a figure eight that was done by early Apollo astronauts. Artemis 1 will not be crewed. Once we see all the operational systems and improve on them, then we'll send astronauts in Artemis 2 to go to that moon, figure eight orbit, and come back and return to the Earth. In the meantime, we're developing a staging area, a gateway, if you will, for which we will, with Artemis 3, dock, and then from the gateway go down to the moon and land and begin that exploration by humans. In the meantime, we will be also exploring the moon with a variety of robotic spacecraft. After Artemis 3, we have designs of increasing our participation of astronauts going to the moon for longer stays, unlike the Apollo program, for which astronauts came to the moon, stayed for a day or so, then returned. Our plan is to have a more sustainable program for which we will stay on longer time periods on the moon, from days to weeks to perhaps months, and therefore really take advantage of our scientists to study the volatiles in these permanently shadowed regions and perform a variety of experiments from the surface of the moon. We'll also be enhancing the gateway over this particular time. This is being planned with a variety of international partners. It will be led by NASA, but we anticipate many more of the space agencies will join us over time. So, what is the future exploration of the moon? Really begins with the ARTEMIS program. We want to be able to continue to do science and exploration on the moon. We want to be able to do this in a sustainable way, live on the moon for longer periods of time, learn to work on a planetary surface. We expect to get into these permanently shadowed regions, understand the volatile history, and be able to extract a variety of things, such as the water. The water in these permanently shadowed regions, we estimate anywhere from 100 to 200 million tons of water, and that actually may be an underestimate. It's only based on our orbital knowledge, so getting down on the surface will be extremely important for us to better understand the assets that may be residing in these permanently shadowed regions. The water we can use to drink, the water we can tease apart, create rocket fuel. We also can supplement the atmosphere that we breathe with the oxygen we will extract out of the water. So indeed, we may lead into areas such as manufacturing. It turns out in the South Pole, there is a large amount of platinum group metals that we detect from orbit, and therefore there may be some important manufacturing activities that we would perform. Well, the future of the moon is bright. I hope this gives you a little indication of the exciting things that we might find. What's in those permanently shadowed regions is really going to be important to tease out, and I hope you will join us along the way. Thank you very much.